Welcome to the Explainer. So, today we're doing something a little bit different. And frankly, it is absolutely incredibly exciting. We are going to craft the ultimate tutorial on quantum physics. But, we're not just going to sit here and list out dry facts. No way. We're actually following expert scriptwriting techniques straight from VMG Studios and the Juno School to decode, literally, the most baffling mystery in the history of science. We're going to build a narrative that finally makes sense of the microscopic world.
All right, first things first, the hook. The Juno School teaches us that to grab your attention, you've got to tap into some pretty powerful psychological triggers. Things like highlighting a failure state. So here is our hook. Everything you think you know about the physical world, how objects move, where they are, how they interact, is about to fail you completely. Because if you're relying on everyday common sense to understand the universe, well, you're actually completely wrong.
And hey, we aren't the only ones who feel that way. This brings us right to Nobel laureate Richard Feynman's famous quote, which perfectly sets up our mystery. Quantum physics just has this reputation for being impossible to comprehend. I mean, even the smartest scientists who developed the math were spooked by it. Yet, it is the absolute most successful scientific theory we have ever had. So, how on earth do we unpack a mystery that even geniuses struggle with? Let's figure it out. To decode all of this, here's our agenda. 1. The double-slit mystery. 2. Superposition and coins. 3. Fast food entanglement. 4. Explaining physics to dogs. And 5. Real-world applications. Section 1. The double-slit mystery. Let's dive right in and prove that our classical understanding of reality is completely broken. Physicist Jim L. Khalili calls this the central mystery of quantum mechanics. So imagine a screen with two narrow slits. If you fire sand through them, you get two simple bumps on the other side. Makes sense, right? If you shine light, you get a striped overlapping wave pattern. But here's where it gets wild. If you fire single atoms, solid matter, they build up over time to form that exact same striped wave pattern. It's literally as if a single atom goes through both slits at the exact same time. And even weirder, if you set up a detector next to the slits just to spy on them, they suddenly act like sand again. They literally change their behavior just because they're being watched. This jarring difference perfectly illustrates the two distinct rulebooks governing our universe. On one side, we have classical mechanics. Sir Isaac Newton's world. It's totally predictable. An apple falls from a tree, a car drives down a street. Simple. But on the other side, when things get incredibly small, quantum mechanics takes the wheel. It's a world that is completely probabilistic. Things are somehow both waves and particles, and the simple act of observing actually changes reality. Moving on to Section 2, superposition and coins. Let's see how these strange rules build into the core concepts of the microscopic world. To understand how a single atom can somehow go through two slits at once, we need a brand new vocabulary. The crucial point here is a concept called superposition. See, instead of an electron being a solid object in one single defined location, quantum physics describes it mathematically as a wave function. This wave represents all the different possible places that electron could be. Superposition simply means adding those waves together. So, until you actually measure it, the particle is quite literally in multiple places, or states, at the exact same time. Okay, I know, that sounds incredibly abstract. But remember, a good script uses relatable analogies. Think of it like a spinning coin. While that coin is spinning on a table, it's just a blur, right? It's neither heads nor tails. It exists in a superposition of both states simultaneously. It is only when you slap your hand down and stop it, when you measure it, that it's forced to pick a single definitive state. It becomes either heads or tails. In quantum physics, this act of slapping the coin down is called the collapse of the wave function. That bizarre, spread-out wave of possibilities instantly collapses into one single physical reality. All right, Section 3, fast food entanglement. Let's explore another mind-bending concept that naturally pops out of all these wave equations. Get ready for quantum entanglement. Imagine two particles interact, and their wave functions get totally mixed up. They become inextricably linked. Even if you separate these particles by, say, billions of miles, like putting one here on Earth and the other all the way in the Andromeda Galaxy, measuring the spin of one particle will instantly, with absolutely zero delay, determine the spin of the other. Albert Einstein actually hated this idea. He famously called it spooky action at a distance because, well, it seemed to imply that information was traveling faster than the speed of light. No way, right? To ground this crazy math, let's use a super visual, everyday thought experiment. Imagine you go to a fast food drive-thru. You order a hot dog and a hamburger, and they hand them to you in two identical unmarked boxes. Right now, those boxes are in a state of superposition. Either one could be the burger, either could be the hot dog. But the split second you open one box and observe a burger, you instantly fundamentally know that the other box contains the hot dog. It doesn't matter how far away that other box is, their fates are completely entangled. Physicist Vlatko the Drawl actually offers this really funny analogy on his blog. He notes that entangled systems are a bit like, well, hippies. Before they're measured, neither particle has a strongly held, defined state. They're perfectly ambiguous. Yet despite lacking those individual definitions, they remain in absolute, perfect harmony with one another. If one jumps to a certain state when it's measured, the other instantly synchronizes. Section 4. Explaining physics to dogs. So here's our biggest challenge. How do we retain all this wild information without drowning in complex math? First, we've got to look at one more bizarre phenomenon called quantum tunneling. Because particles are actually probability waves, when they hit a solid barrier, that wave doesn't just stop instantly. It actually decays exponentially inside the barrier. And if that barrier is thin enough, a small part of that probability wave exists on the other side, meaning there is a literal, physical chance that the particle will just pop into existence on the other side of a solid wall, completely bypassing it. To explain concepts exactly like this, physics professor Chad Orzel wrote an entire book framing quantum mechanics as conversations with his dog, Emmy. Now, Emmy the dog, being incredibly practical, wants to know if she can use quantum tunneling to magically pass through the neighbor's solid wooden fence to catch the bunnies on the other side. It's a hilarious, playful analogy, but it highlights a really crucial point. While quantum effects are the absolute, unbreakable law for tiny electrons, applying them to our macroscopic, everyday world, like a dog trying to phase through a fence, is totally absurd. The probabilities for large objects are so infinitesimally small that they effectively never ever happen. And to explain the strange nature of quantum measurement, where just looking at a system forces it to change, we can use another awesome analogy. Picture a nervous, mumbling soldier who's totally unsure of his orders. He represents a particle in a fuzzy state of superposition. Then a strict army lieutenant walks in and screams, "Did I make myself clear, soldier?" The terrified soldier instantly snaps to attention and yells, "Yes, sir." See, he's forced to collapse his indecision into a single crystal-clear stance. The measurement, the shouting lieutenant, literally forces the quantum system to forget its previous fuzzy state. Section 5. Real-world applications. All right, we've set up the mystery, used some fun analogies, and now we arrive at the ultimate value proposition. Why does any of this spooky science actually matter to your everyday life?
Because listen, quantum mechanics isn't just weird blackboard theory. It is the literal foundation of modern technology. The GPS system in your car, it relies entirely on the quantum mechanics of atomic clocks to keep perfectly synchronized time. When you go to the hospital for a scan, MRI machines use quantum magnetic resonance to look inside your body without a single incision. Solar panels rely on the photoelectric effect, a quantum phenomenon where light behaves as quantized packets of energy to knock electrons loose and create clean power. Even the semiconductors in the device you are using to enjoy this exact explainer right now, they only work because we understand how electron waves move through silicon.
Just to put the sheer precision of this science into perspective, think about this staggering number: 33 billion. A quantum logic atomic clock built by the U.S. National Institute of Standards and Technology is so unimaginably precise that it won't lose or gain a single second in 33 billion years. That is more than twice the current age of the universe. It's absolutely mind-blowing. Finally, scriptwriters tell us you should always end with a lingering thought. We've seen how the world at the smallest level is basically a blurry, probabilistic soup of waves that only solidifies into reality when we actually measure it. Yet, this spooky, unpredictable realm perfectly dictates the solid, classical world you walk through every single day. So I'm going to leave you with this provocative question to ponder. If everything you touch, see, and interact with is fundamentally built upon a foundation of fuzzy, shifting probabilities, how much of your everyday reality is just an illusion? Thanks so much for exploring the greatest mystery in the universe with us today. Keep questioning and keep learning.